All right, guys, so this is IS number 15, the third page. So this is the big ideas for that first part. The first big idea has to do with learning target number 1, which is about the conditions for constructing a confidence interval for mu. So it's the same as the conditions for proportions, except for number 1, number 2. You have to have a random sample and you have to have that 10% condition met so that N is less than 10% of the whole population. Where things change is how you check that a normal model fits the sampling distribution. For proportions, you had to check that large counts where it was N times P. Well, we don't have P here, right? We don't have a proportion. So there are 3 different ways to check it. One is that the population distribution is approximately normal. If that's true, then the sampling distribution of the sample mean will be normal. The second part is that N has to be greater than or equal to 30. So if your population distribution isn't approximately normal, but your sample size is greater than or equal to 30, the central limit theorem applies, normal model's good. If neither of those fit, then the third option is to check that the sample data shows no strong skew or outliers. And this is a pretty loose condition. If there's a slight skew, if the skew is not too bad, or if there's maybe like one outlier, the normal model will probably still be a good fit for the sampling distribution. It's only when you have a strong skew and clear outliers. The unfortunate part about this last part is that you actually have to make a histogram or a dot plot of the data. So we'll see an example of that later in the notes. Okay, so those are the 3 conditions you have to check: random, 10%, normal. There are 3 different ways to check the normal condition for confidence intervals for means. So then the second part is about critical values. This is the part where confidence intervals for means differ from proportions. Instead of using Z star for critical values, remember we're using T star. Okay, T star is used for confidence interval for means. We learned something new. The degrees of freedom are equal to N minus 1. And I realized that I didn't really explain that well in the previous video. So degrees of freedom are a little bit more complicated than this, but the long story short is that this is how many data values would be able to be determined by or be able to be made up to calculate a certain measure. So if we're wanting to calculate means, we could make up all 29 of the Oreo weights. But once we've made up 29 of them, if we know what the sample mean needs to be, then the 30th sample value is determined. Like I said, that's long story short, but it's not really important that you understand where degrees of freedom come from. If you really want to know, you can read the description in the book again. You just do need to know that the formula for calculating them is N minus 1. Okay, so then to find that critical value, you have to know degrees of freedom, and then you use table A3 with your degrees of freedom in the area of the tails for whatever confidence level you're looking at to find that T-star value. Also keep in mind on this table A3, it goes degrees of freedom all the way 1 through 30, and then, this one actually goes to 40, which is nice. But then at 40, it starts skipping around. It gives us 45, 50, 60, 70. So once we get to these higher sample sizes, we should round down to get a conservative value for T-star if we're using table A3. But the better idea, if you have a large sample size, is to actually just use technology to use that inverse T function from the calculator. You take that left tail area plus your confidence level. So for us, remember that was 0.025, right? That 0.05 divided by 2 plus our 0.95. That was how we figured out that area we needed for this function with a 95% confidence level. And then you include your degrees of freedom. Okay, so let's check our understanding of those ideas. Again, the new parts are finding that critical value and then being able to check the normal condition. So those are the 2 things we're going to focus on. It says use table B. Oh, I have a mistake. I'll fix it for you guys. Should say use table A3. Sorry about that. Use table A3 to find the critical value T-star that you would use for a confidence interval for a population mu in each of the following settings. If possible, check your answer with technology. Okay, so it says, and find a 98% confidence interval based on a random sample of 22 observations. That gives us all the information we need. N is 22, confidence level is 98%. So I'm going to think about the tail area, or the area of the tails first. I'm going to take 1 minus my 0.98, right? 1 is the total area under the curve. 98 is that going to be my middle area. So the area of my tails is going to be 0.02. Again, that's the area of the tails. Let's check. Is 0.02 on table A3? Area of two tails, 0.02. Okay, I'm good. And then I'm going to calculate my degrees of freedom. So degrees of freedom are equal to n minus 1. 22 observations, so n is 22 minus 1, of course, is then 21. Okay, so I'm going to use those two things together in table A3 to figure out what my t star value is. Okay, so 0.02 and 21. I'm going to find 0.02 up here at the top first and then follow these degrees of freedom down here to 21. So I'm lining up 0.02 with 21. Looks like it's 2.518. Okay, so T star is 2.518. So when I'm calculating a confidence interval, specifically a 98% confidence interval based on that random sample of 22 observations, when I go to actually plug into my specific formula, this is the T star value that I will need. Okay, but it does say to check your answer with technology, so let's do that. Okay, again, I'm going to use that inverse t function, but in order to do that, I need the left tail area plus my 0.98. So I'm going to try to write a little bit maybe simpler way to calculate that. We could take our area of the tails, my 0.2, divide that by 2, and add 0.98, the middle area. So 0.02 divided by 2 would be 0.01, plus 0.98 would be 0.99. Okay, so I would plug that into my calculator, 0.99, and then my degrees of freedom, which are 21, and let's see what I get. Okay, plugging into the calculator. So I got a second distribution again to find that inverse t function. It's the fourth one. I'm going to plug in 0.99 and degrees of freedom of 21. All right, look at that. I get 2.5176. If I round to 3 decimal places, I get 2.518, just like I got from my table. So my answer is correct. Okay, here we go. Let's move on to a 99% confidence interval for a simple random sample of 71 observations. Remember, SRS stands for a simple random sample. Okay, so confidence level and n are what I need here. So I'm going to do the total area of the curve, 1 minus 0.99, that's the middle, and I get 0.01. That is the area of my two tails. Okay, and then I need the degrees of freedom, which are equal to n minus 1, or 71 minus 1, which is 70. Oh, minus 1, not 7. Sorry about that. Okay, so I use those two things together in table A3 to give me a T star value. Okay, let's figure out what that is. So 0.01 is my area of tails, 70 is my degrees of freedom. Okay, 0.01 is up there. I follow this all the way down to 70. Okay, I get 2.648. 2.648, I think that is my answer. Let's check using technology. Okay, again, so my area of both tails is 0.01. I have to divide that by 2 and add that number to my middle area of 0.99 to figure out that total left area. So 0.01 divided by 2, I'm just going to check on this. 0.01 divided by 2 will be 0.005 plus 0.99, 0.995. Okay, so that is the area I'm using in my inverse t function. So inverse t, 0.995, comma, 70 for my degrees of freedom. Okay, so let's see if that's correct. Okay, I'm gonna go to second distributions, go down and select inverse t. This time I want 0.995 for my area and degrees of freedom of 70. Please make sure you're careful to change your degrees of freedom to the problem you're actually working on. Okay, paste that in. And we get 2.6479, which again, if we round, is 2.648. All right, 648. We checked with technology and we are correct. So before I move on to the next problem, I just want to make a quick note about finding T-star values. I really do think that the table is the easier way to find them if your exact degrees of freedom is listed. It's just easy to make a mistake trying to calculate the area that you need to put in here for this inverse t function. But if your sample size is not listed on the table, then I think the technology is worthwhile. Okay. So number 2 says, Judy is interested in the reading level of a medical journal. So she records the length of a random sample of 100 words. Okay, I'm already thinking my condition of random is met. And there's my sample size. The histogram displays the distribution of word length for her sample. Determine if the conditions for constructing a confidence interval for a mean have been met in this context. So I don't have to construct the whole confidence interval. I'm just determining if the conditions have been met. Okay, so remember our first condition up here from our big ideas is the random condition. So I'm just going to write that out. And this is how I will expect you to check your conditions on all the confidence intervals you do. Do I have the wording in my problem somewhere that I had a random sample? Yes, it says random sample of 100 words. So that condition is met. And remember, I use a check mark to indicate that the condition has been met. Okay, so condition number 2, looking back up at the big ideas, is the 10% condition. I'm just going to write 10%. That's fine. Then I have to show how I check that. So n is 100 this time. That is, well, is it going to be less than 1/10 of the population? Well, first of all, the population, I'm looking at the reading level of a medical journal, so I'm probably looking at all the words in the medical journal. So is 100 1/10 or less than 1/10 of all words in this medical journal? I don't know if you've ever seen a medical journal before, but they are very wordy. So yes, I think 100 is definitely less than 1/10. There's more than 1,000 words in a medical journal. So that condition is met as well. Check. Okay, then the third condition is whether or not we can use a normal model to approximate our sampling distribution of X bar. Okay, so there are 3 different ways we can prove that. If the population distribution is known to be approximately normal, well, it doesn't say anything about the population distribution. I don't know about the distribution of word lengths, so that doesn't work. Then I check, is n greater than or equal to 30? The central limit theorem would apply. N is 100, so that is true. N equals 100 is greater than or equal to 30. So my central limit theorem applies. All right, that's my third condition. It's been met. I would say all conditions have been met. Okay, so why did they give me this histogram? Well, I gave it to you so that I could point out what we would do if the sample size was not greater than or equal to 30. Remember that third possibility is that the sample data shows no strong skew or outliers. So if we look down here at the histogram, we see that it has a slight skew to the right, but it's not very strong. It doesn't appear that there are any outliers. So we would probably say that this is approximately normal. This would be okay. Or I'm sorry, not that it's approximately normal, but that it shows no strong skew, and we could go ahead and say that the normal model would be a good approximation. In your test questions, I will actually give you the sample data in some sort of distribution in a histogram or a dot plot for you to make the decision whether or not there's a strong skew or outliers. However, we are going to see some problems on the next page where we actually construct that dot plot ourselves. But again, you will not be required to do that in your test. You'll just have to make the decision based on the dot plot or histogram that is given to you. Okay, see you in the next video.